All right, so in this example, we're asked to find the Riemann sums for this integral from 0 to 2 of e to the minus x squared over 8 dx. Okay, so we have n equal 2, right? And we're integrating from 0 to 2. So if we divide 0 to 2 into two parts, then each subinterval is one time unit. Well, I guess it's not delta t, is it, in this case? It's x, so I should probably make this x. We have a delta x of 1. Okay, so that's the width of our subintervals. All right, so I've gone through the calculations, right? So we basically are breaking this interval from 0 to 2 into two subintervals. So for the left integral, we're just going to take the two left-hand data points times the width and add them together, right? For the right, we take the right-hand data points times the width, which is 1, add them together, and so on, right? And then for the midpoint, we're just going to take the midpoint. So we're going to have midpoint at a half, and we have a midpoint at, so this is at 1/2, and a midpoint at 3/2, or 1.5. Okay, so just evaluate the function. And in this case, I'm taking f of x is equal to the integrand, which is e to the minus x squared over 8. Okay, so you can compare your answers. Now let's take a look at whether or not these are overestimates or underestimates. So in part E, we have a graph of the function. And we're integrating from 0 to 2, right? So we're trying to find this area right here. And just by eyeballing it, it looks like in that interval, it's obviously decreasing, and it also looks like it's concave down. So so just by eyeballing, we could say it's concave down, and it's decreasing. Okay, so based on that, we can evaluate whether or not these Riemann sums are over or under estimates. Now, there actually is an inflection point here. If you take the second derivative of the function and evaluate it, find the inflection point, there's actually an inflection point here at 2. So, but you can evaluate it if you want to find the inflection point, but you can take my word for it, there's an inflection point at 2. All right, so it's decreasing and concave down. So let's go back up to our Riemann sums and evaluate them. So the left-hand sum is going to be, and because it's decreasing, right, it's going to be an overestimate because the left-hand data point is going to be higher. Overestimate, right? Because f of x is decreasing. Oops, decreasing. Okay. And the right-hand sum is going to be an underestimate, right? Underestimate. And again, it's just because that right-hand data point is always less, right? Because the function is decreasing. So because f of x is decreasing. Okay. Now the midpoint rule is going to give us an overestimate. Now you can draw it out if you want to. If you ever forget, because I would never remember these things. I oftentimes have to draw these things out. But because it's concave down, right, the tangent line at the midpoint is going to be above the curve, and so we're going to get an overestimate, right? And that's because f of x is concave down. Okay, and then the trapezoid rule is going to give us an underestimate. So underestimate, estimate. And again, because it's concave down, so that line that connects the two data points is going to be below the curve. And so we're going to get an underestimate because f of x is concave down. Concave down. All right, so that takes care of that example. And now we're going to move on to looking at a little bit closer at the errors in the trapezoid and the midpoint rule. And I'll meet you for the next, and we're going to talk about Simpson's rule. And then we'll go to the next example. So read through this next stuff. Now that's actually a more detailed explanation in your book of analyzing the errors in the trapezoid and the midpoint rules. But by analyzing the errors in the midpoint and the trapezoid rules, that's where Simpson's rule comes from. So take a look at that, and I'll meet you for the next example.